Now this illustration deals with method 2 to determine the available short circuit current. In accordance with 110.9, 110.10, and 110.124. Now, notice again, we're determining the available short circuit current at the terminals of the overcurrent device at the service equipment. Now, this is the method that when I worked for a firm that we were trained to use. Our designing senior engineer and contractors said this is the best, more accurate method to use. And you can use your NEC to do this. Now, step 1, we're going to again find the available short circuit current at the transformer, which we've already done in the step 1 previously, and come up with 16,067 amps. Now, step 2, we're finding the resistance of a 100-foot run of 250 kc mil, and we're using the table A of the annex in the Stallcup's electrical design book, or you go to the table 9 in chapter 9 of the NEC, and you can do the same thing. Now notice the resistance of a 250 kc mil conductor pulled through rigid metal conduit or metal raceway. Notice it's 0.054 in step 2 times a 100-foot run divided by 1,000, because the table 9 is based upon 1,000 foot or less, and we're less than 1,000 foot, we're 100 foot. So when you do the math, the resistance then of that 100-foot run is 0.0054, as you see in the step 2. Now you've got something to work with, see? Now step 3, we're going to determine the voltage to ground divided by the available short circuit current of the transformer. So what is the voltage to ground? Well, it's a 480 277 volt service. So the voltage to ground, when you divide 480 by 1.732, the square root of 3, we come up with 277 amps. So 277 volts, divided by 16,067, we come up with the resistance for that 100-foot run of 0.01724. Now we move to step 4. We calculate the total resistance. And notice the run of 250 kc mil conductors and rigid metal conduit is 0.0054. We obtain that in our step 2 calculation. The resistance now of the transformer, good rule of thumb method to use here. I know you can use software and get it closer. Step 3, we calculated the resistance of that 100-foot run is 0.01724. So notice we take the resistance of the transformer at that value, add those two resistance together to get the total resistance of the overall run of the wire. We come up with 0.02264. That's including the resistance of the transformer and the resistance of the 100-foot run of 250 kc mil THWN copper conductors routed through metal conduit. Now to determine in step 5 what the short circuit current is, we take the voltage to ground, divide it by the total resistance. So the voltage to ground, if we get a ground fault, the voltage is 277 volts of the 480 volt system, divided by 0.02264 total resistance. The available short circuit current then is 12,235. So you can well see here that either method 1 or 2 that's used, one comes up with 11,000 and something. This method comes up with 12,000 and some amps. But notice we're still using either a 15 KA system if you can purchase it. If not, you're using a 20,000 amp system or 20 KA system. And notice either method, you come up with about the same thing in the solution and the answer. But the people that I worked under, the engineers that I worked with, the electrical contractors I worked with, plan checkers and so forth, they all seemed to feel that this method 2 was the best method to use by electrician and so forth, because they could go to their code book and perform this calculation just using their code book and a handheld calculator. And again, if you purchase the Stallcup's electrical design book, these formulas and all this is there. The tables are there in the back of the book in the Annex A for you to handily look at. But you can do this just with a code book and your calculator by just looking at this illustration. So this illustration 6-34, little c is in car, demonstrates the method 2 to determine the available short circuit current at the terminals of the switchgear as required in the NEC 110.24.